Hi everyone, in this video I'm going to walk you through the second homework set. But before doing that, I'd like to deal with the issue in homework format because you are supposed to submit everything in one file, not separate files. So if you are doing this in R, you are supposed to copy and paste all the code at the end of the homework as appendix, not in a separate file. Well, that's all about the format issue. So now let's dive into the homework. This one is about how to get a box plot. We talked about how to deal with the univariate case in which we only have one variable, but in this case we get 4 variables. In this case we have already typed in all the data here, and the only thing that's worth talking about is a variable name. So if you have something like Big Bear or Loop Hill, you have to connect these words by an underscore, and if you do it like this, it will not work. In this case, we want to type in the box plot, which is the command we want to use, followed by all the variables we want to plot. In this case, it is everyone. So now if we select all the code here and run it, as you can see here, we have a side-by-side box plot. But the name of each variable is 1, 2, 3, and 4, which is not that informative. So to fix that, we can assign a name for each of the variables. And after typing all the name here, we can rerun this line of code. And now as you can see here, each of the variable has a name. Conclusion, considering the geology of 4 locations, we can say that as we are going north, the squares, they are getting longer and probably bigger. So that can be your answer for part B of question 2.5.2. You are supposed to generate a scatter plot with R code for the data that you are given. So let's see how to do it. As you can see here, I already typed in part of the data, but not all of them because I'm lazy. But you are supposed to type in all the data that you have, 12 pairs, and more importantly, you have to make sure the length of X matches the length of Y. This is very important because when you are plotting a scatter plot, you are assuming that everything shows up in pairs. Now, after that, you want to type in X, comma, Y, and now you run the whole thing. As you can see, you get a scatter plot. Okay, in this question, you want to calculate the mean and standard deviation. So this is how to implement it. So in this case, we call our data ATP and run this line of code. This is how to calculate mean, pretty straightforward. And in order to calculate standard deviation, the keyword you want to remember is SD. And the standard deviation is 0.184. Well, this one is going to be a little tricky if we insist on using R, but it's still going to be kind of fun. So let's see how to do it. As you can see here, I already typed in all the data in the CK dataset, and because the textbook asks to find out the percentage of the observations that falls within one standard deviation of the mean, so we have to first and foremost find out the mean of CK and the standard deviation of CK. So as we can see here, the mean is 98 and the standard deviation is 40. We want to find out in the CK dataset how many data that actually falls in between one standard deviation around the mean. So in other words, we want to find out how many observations out of the 36 CK observations are actually in between 57 in this case and 138. Well, of course, you can go ahead and eyeball each of the observations. For instance, 25 in this case is too small. It's not in between the range, so we cannot count that. But 62, well, that is a good one because it's between the range we are talking about. You can, examine each of the observation and count how many of the observations are actually falling in this range. So this is actually a path that you can go. But that is certainly not the best way to do it because we don't want to go down the rabbit hole by looking at each of the observation manually, which has to be a pain. So here is a shortcut. Let me first give the boundaries a name. One of them is called left and one of them is called right. So the thing is, we want to compare every single member in CK with the boundary. So this is how to do it. We want it to be greater than the left boundary. So if we stop here and run this line, you are returned to a lot of booleans, so to speak, yes or no answer. So in this case, let's say the first one, which is 25, and what computer does under the hood is to compare 25 with the left boundary. And as you can see here, because 25 is smaller than 57, so it is returned as a false because it's not greater than the left boundary. And what about the second observation, 62? Well, it is greater than the boundary, so that's why you got a true returned. And actually, you can do arithmetic for these booleans. For instance, if you want to see how many yeses you got in total, so you can sum it up, and you get 32 of these qualified observations. Well, of course, that's not the end of the story because we want to count how many CK observations actually falls in between left and right. So in order to do that, we have to modify this condition by putting one more condition, CK is smaller than right. And don't forget to put a parenthesis to make the syntax clean and explicit. So as you can see here, we get 26 of the observations. That is both greater than the left boundary and smaller than the right boundary. And that is 26 of them. And because the question asks for percentage, we use 26 divided by 36 based on the background information provided by the textbook. So in this case, we get 0.72. And similarly, if you want to work on the second part of the question, which is to calculate how many observations percentage-wise falls in between two standard deviations of this, you can just modify this code script by doing this. Two standard deviation here, two standard deviation here. So now let's calculate this again. Well, we have 34 of these observations that lives between two standard deviation around the mean, 34 over 36, and in this case the percentage is 94%, which is pretty consistent with what we might have concluded based on the empirical rule. If you can recall that, we will have 95% of all the data theoretically that is included within two standard deviation around the mean. In 2.S.7, you are supposed to calculate mean and median and plot a histogram, which are all pretty standard stuff, I think. But you might have some trouble in marking the positions of mean and median if you are using R. Let me show you how to do it. So as you can see here, I have typed all the data here of seizure. As you can see here, the mean and median, they are different. Next, you want to plot a histogram for the data that you've got. The keyword here obviously is hist. So this is the histogram of seizure. In order to mark the mean and median on the histogram, AB line is the keyword or the command to implement this job. So you want to plot a vertical line, which is the median 0.5, and probably you want to give it a different color, like the red one. So if you run this line, you have marked the median. And similarly, you can mark the mean on this histogram as well. In this case, it's 2.75. And we want a different color probably, so we can run this line. And now we successfully have marked the mean on the histogram. The point of this question is to show you the power of transformation, because sometimes we don't have a data set that looks quite normal shaped, but we want to transform it into a bell-shaped distribution. And a log transformation is something that we usually do and works pretty well. So as you can see here, I have already imported all the data and scanned all the data here. But the first thing we want to do, as we talked about before, is to define some breakpoints or equally sized bins and try to count how many observations falls into each of these equally sized bins. So we have to define these breakpoints here. And as the textbook have suggested, we want a step that is 10,000. So the incremental step every time is 10,000. And make sure that the last breakpoints that you have defined, it has to be greater than the maximum of your data sets. So that's why we have 140,000 as the last point for the breaking points. So the next step is, to use that cut function to cut our S17 data based on the breakpoints that we have just defined. And of course, we want to put it in a table so that we can have a nice representation of all the breaking points, or the frequency distribution, so to speak. Now let's run these two lines. We get this frequency distribution. As you can see here, it is kind of problematic because it is not evenly distributed in each of the bin, and most of the data has been congregated in the first bin, which is, from 0 to the first 10,000, and there are 24 observations that falls in that bin. So we are going to solve that problem by doing a log transformation. Well, the next thing we want to do is plot a histogram for the data that we've got, and since we already got the breakpoints, why not utilize them? So to run this line, we can get our histogram of all the data. As we can see here, most of the data is still congregated around 0, which is pretty consistent with what we have observed from that frequency table. Next, you might be wondering, is there a better way to define these breaking points rather than type them out for each of the single observation? Well, actually there is. So there is actually a smarter way to define this, which is by a sequence. Let's see if we can start with 0 and end with this number. Let's copy and paste and make the step being 10,000. Let's run this line. We have got the same sequence as we have defined before without doing all the typing. The next thing that we want to do about this data is, because of the weird shape, we want to transform it into a shape that we can work better with. What we are going to do is to take a log transformation. There is one caveat in this case, because by default we use a natural base, not a base 10 log. We have to use this function, log 10, not the log function, again because that log function is natural base. We have to do the transformation for the data here and call it transformed data. What we want to do next is to construct a frequency table for the transformed data, but before that, let's take a look at it. So as you can see, after the transformation, the data is becoming much normal. So in order to create a frequency table, we have to look at the range of all the data. As we can see here, our data ranges from 0 to 6. So actually we can place 6 bins from 0 to 6. So again, as we talked about, we can make a sequence by this shortcut from 0 to 6, and step is 1. So that are the breaking points for our transform data, so that we can distinguish these two versions of problem. One of them is transformed data and one of them is regarding untransformed data, so to speak. So what we want to do is to construct a frequency table based on the transformed data. So let's cut the transformed data by transform the cutting points and make a table out of it and run this line of code. So as we can see here, the data is more evenly spaced. Okay, the last thing we want to compare is the mean of the log and the log of the mean. So in this case, we first calculated the mean of the data after log transformed them, and we got 3.35. And what if we first take the mean of the original data and then take the log of their mean? So as you can see here, there is slightly a little difference here. And the second case is the median. We want to compare the median of the log and the log of the median. So the first one is we calculate the median for the transformed data. We get 3.46, and the median of the original data is like 3,000. And what if we take a log 10? As you can see here, they are pretty close. As a matter of fact, median is actually resistant to this kind of operation, because calculating median is only about finding the observation in the middle, while this kind of transformation like log transformation or exponentiating all the numbers, it does not change the order, so the median actually should not change at all. Well, I guess this one is simple, just to find out all the groups that is qualified. For instance, part B, what is the probability of a randomly selected person is in between 20 to 49. Then you find all the age groups from 20 to 49, and that would necessarily include 3 groups, from 20 to 29, from 30 to 39, and then from 40 to 49, and you are supposed to add up all the probabilities. So I guess that's it. In this question, actually we can split it into two different scenarios. First of all, the student has prepared for that question and the student has not. So this is a natural scenario that we can fit in the tree diagram. So the first branch, let's use P to indicate that student has actually prepared, and PC means she has not. So we can fill in the probability for this tree diagram. This is 0.4 according to the background information, and this is 0.6. And in this case, probably it's 100% because if she knows the answer, she knows the answer, and this is 0. But for this second branch, it's trickier because it's 0.2 for a random guess to work, and it is 0.8, which means random guess doesn't work. And as usual, in order to find out the intersection along the tree, what we actually do is to multiply along each branch. So in the first branch, we get 0.4 multiplied by 1, which is 0.4, which is the probability of both has guessed the exam, both has prepared the exam and made it work. So which is and right. And the second case is 0.4 multiplied by 0, which is 0. But what makes more sense here is the second branch. If this girl has not prepared for the exam but somehow made a random guess that is right, there is still the chance, a real chance, that she can make it right. But more often than not, if you make a random guess, probably it will not end well. So that is 0.48. So as you can see here in these four scenarios, two of them, she made it right. In order to find out the probability that she can make it right at the end of the day, we have to consider these two scenarios, so which is given by 0.4 plus 0.12, and that is 0.52. So the probability that she can make it right is 0.52. If you again look underneath the hood, actually it's comprised by two different scenarios. So this one is, I think part A and B are pretty similar, so I will just talk one of them. It starts with 1,000 women. 100 is really pregnant, so, 900 is not pregnant. And from the background information, if you know that the woman is really pregnant, there is 98 chance that she will test positive. So that means out of this 100 women, 98 of them will get a positive test. So let's use a plus sign to show that they got a positive test, and this P is for pregnant. There will be 2 of them who get a negative result. And we can take a similar look at these 900 women who did not get pregnant. Among them, 99% of them will get a negative test result. So we can get 99% multiplied by 900. And on the other hand, there will be some of the women still get a positive test, although they are not pregnant, by 900, and that leaves us 9 of them. And in this case, you get 891. At the end of the day, we don't care whether you're pregnant or not. We only care generally what is the likelihood to get a positive test. So as we can see here, there are 2 resources to get a positive test. One of them is, being really pregnant. But you can also get a false positive, like here. So these are 2 resources you can get a positive test result, regardless of the reason. And at downstairs, we have like 1,000 of subjects here. So if you do the math, it's 107 over 1,000, and the probability is 0.107. And this one is still quite similar to 3.2.5 and 3.2.6, but I really want to hammer it in. So let's just do one more example. So we can start with the 10% of the population who has the disease. So we get the diseased group and the non-diseased group. And the next question we ask is whether you will get a positive test or not. As you can see here, if a person really has it, we will have a 92 chance of finding it. So among these 10% of people, 92% of them will be tested positive. and there will be 8% of them, unfortunately, will test negative. So on this side, among these 90 people who really don't have it, the probability that they will correctly get a negative test is 94%. And there is still obviously 6% that they can get a positive test, which is a false one. We can multiply along the branch. So in this case, the first tree branch, the probability of both have disease and get a positive test result is obtained by multiplying these two probabilities. And similarly, the probability having disease and having a negative test, which is given by 8% multiplied by 10%. So, if you look at this question, it asks you what is the probability that a randomly chosen person will test positive. So, in this case, we only care about the plus sign here, which is for the positive test. So, as you can see, this is the first category, and this is the second category that is qualified. So, the probability of finding a positive test is comprised by these two categories. So whatever this number is a probability that a random person will test positive. The second part of this is a conditional probability. The probability that a random person does test positive. Given that fact, what is the probability that this person will really have the disease? You might have remembered this is given by the intersection of these two events divided by the conditional probability. So in this case, we have already figured out P plus from part A, which is this one. So whatever this is, let's plug this in on the denominator. What happens upstairs is probability of D and plus, that is given by 92% plus multiplied by 10%. First one is what's the probability of someone in this case that smokes. We just want to find the total count of those who smoke divided by the total number of sample. So in part B, you want to find out the conditional probability given the fact that this person has high income and what is the likelihood of he or she is a smoker. So what we want to do is to just focus ourselves on the high income group and use that as denominator, which means we disregard anyone else. And among this group, we have like 247 smokers. And the last thing is to find whether smoking is independent from the social income. We want to compare the quantity that we just obtained from A and B. So if these two quantities are equal, then it means it is independent. Because given the fact that somebody has a high social income does not impact the probability that someone is smoking. Having a higher salary has nothing to do with the smoke status. But if you find that A and B are different, and then that means having a higher income have something to do with the smoking status, because knowing the status of this part changed the probability of smoking. So in that matter, it is dependent. So in this question, we continued to use the data in 3.1. First of all, what's the probability of someone is both, having low income and smoke? So we want to locate the number from that table, which is 634, divided by the total, which is 6549. We do not disregard anyone because in this case there is no conditional probability statement. And in the second part, you want the probability of someone is not from low income group. So in this case, we want to find the total number that is not from the low income group and sum them up. 1954 plus 2115 divided by still the total number of sample. In the third question, it's asked what is the probability that someone in this study is from the medium income group. So still we have the 1954 from medium group and divided by 6549. And lastly, what is the probability that someone in this study is from the low-income group or from the medium income? As long as he is not from the high-income group, he would be qualified. So this is how to use a contingency table and find out all the desired probabilities.